Okay, so for the next section, we're going to have the chance to play around with some data that's been automatically processed and is available online in applications. So this is the data on the Volcano Deformation portal. If you have a browser accessible, you can put in that link and have a look just now and look along with me. I'm going to give you a little bit of an introduction to what the aim of this is and what the functionality of the different tools are online. At its simplest level, what it allows you to do is go through and examine individual Sentinel-1 interferograms that are processed over volcanoes all around the world. You can flick through between the interferograms, assess them. You can also follow a link to them, download them, and analyze them yourselves. More usefully, what you can do is do on-the-fly time series and topographies, and transects cut across the topography and cut across the interferogram to look, for example, at the relationship between a particular a signal at a particular point and time, or a signal at a particular point and local topography. And then finally, it's got some implementation of some machine learning predictions that you'll hear more about this afternoon, which flag up activity which is similar to volcanic processes, and this is worth a particular look. So the aim is to make satellite deformation measurements more accessible. Originally, it was designed to be something that volcano observatory scientists could use. And the aim of the tools is not necessarily for doing a thorough analysis of the data, but more like a quick look, a kind of initial check to see if the data quality is sufficiently good for some analysis, and if it's kind of worth downloading and making some further steps. So it doesn't need any local processing, and the preliminary analysis can all be done on the fly online. So freely available around the world just now are the volcanoes that are indicated by green circles. The darkness of the color within the circle shows you the number of interferograms that are available to play with. So you can see that the very darkest color there is more than 800 interferograms. And actually, most of the ones that are available have that sort of number. And my aim for about the next 40 minutes really is just to give you a chance to play with those tools to kind of practice some more practical skills in making sense of interferograms, because we've had a lot over the last few days on the theory of INSAR, and you've been introduced to quite a range of different tools. The point here is essentially just to see what the data look like and play with it a little bit. So what I suggest that you do is try and think about how you're going to decide whether the signal that you find when you're looking on the website is real, as in it's kind of a volcanic process or tectonic process, or it's one of the sources of noise that we discussed earlier. So you might start off by saying, is the signal independent of topography? So you can do that by, first of all, looking at the shape. You're going to have a tool which allows you to look at a Sentinel-2 image. So that's an optical image. It'll give you a feeling of what the landscape looks like on the right. And then you'll have the topography on the left with the interferograms placed on top. You can make transect profiles across it to compare that. Then you might want to ask a question like, is the signal associated with more than one acquisition? If it just appears once, or is it something that's persistent? And do you see it in multiple look directions or multiple tracks? You've got a time series tool. You can do that to ask more sophisticated questions. Does the time series show any potential signals? Are those signals correlated with topography? Do you see seasonal trends in the time series? Is that dominantly what you look at? Is it very sensitive to your choice of reference pixel? Because you remember that all INSAR measurements are made relative to a point, and they're only as good as the stability of that reference point. And is it correlated with land cover? Is it possible that you're looking at something that might be related to phase bias or a fading signal, or is it genuinely useful? So you can go through and interrogate these things with tools on the portal. So you can make some profiles to assess whether they're real. You can look at whether you can reduce seasonal noise, for example, using spatial temporal filters. You can change your reference pixel area, both by picking particular points and moving it around, also by increasing the size of the reference area to see if you get a less noisy result. And you can compare to the Sentinel-2 imagery to check whether you only happen to have signal over dense forests, say. So to give you an example of some of the data on the portal, this is actually from Pedro Espin's PhD work looking at Sangai. The automatically processed results that we initially had looked a little bit like this. And as a quick look, it's enough to show that there's something interesting potentially there. You had a good long-term uplift with some blips in it. But by spending more time in developing a more robust network, Pedro was actually able to extend the area coherence and get a much better signal, more useful signal, which could be interpreted in terms of magnetic sources. Once you've got that sort of information out from your own analysis, you can resolve components of motion, which is not something we currently have a tool for, work out the direction of displacement. So here at Sangai, there are a couple of processes going on. There was a downslope movement associated with fresh products in this quebrada. And then there's also a magmatic signal, which you can see clearly here in the horizontal displacements. So the movements outward from the center of the volcano. Okay, there's a practical after the break. So I'm going to move across to the Comet website, Deformation portal now, and I'm going to give you a kind of talk through one of the volcanoes. All right, I'm going to start off with, let's look at Wolf in the Galapagos. So there's a database component to this website, which I have to confess is actually quite out of date now, but there is some information there about previous observations of deformation at Wolf. And then you have a tab here, which is for exploring sentinel imagery. This first bit here has all of the different frames for which there's data available. If you are already familiar with the LIXAR conventions, if you have an A close to the beginning here, it's an ascending frame, D is the descending frame. And just to give you a quick look, this is your cumulative displacement across a time span from 2017 through to 2025. So pretty nice complete data set there. And also a nice big signal, which is associated with an eruption. If we switch over, we can see the equivalent data for a descending track. There you go. You can see that it picks up slightly different processes. It also spans the full time period. And then you've got two other ascending legacy tracks. So you've got some options here depending on the sort of browser you're using. This is the highest data resolution that you can look at. You can move across and see the low one. If you want to look at it from somewhere with a less stable internet connection, that helps. We can apply a GACOS correction to the data, hopefully. Take a minute to load. There we go. In this case, it makes very little difference because the GACOS correction in the Galapagos is not hugely helpful because it's an oceanic island and you've got water vapor signals which are kind of highly turbulent and associated with the island topography. And at any rate, the deformation is so large that the noise is quite low. And you can, at the moment, this is a filtered result. If I switch it to unfiltered, you can see it's very slightly noisier. Actually, it makes relatively little difference at Wolf Volcano. You can have a look at the how displacement varies through different parts of the image. So, for example, in the center of Wolf Caldera there, you can see you've got this beautiful long-term uplift, which went all the way from 2016 through to 2022. Guess what happened in 2022? Quite a big explosive eruption. It was unusual for the Galapagos and being very, very explosive. And then you've got this is, I think you asked me about cycles of displacement. Wolf, I think, is one of the few examples where you actually do have that cycle that's sort of predicted and people talk about of like uplift, corruptor subsidence, and immediate reinflation. But I would say it's kind of unusual in following that quite so well. And then we have reinflation. You can see it's going on quite rapidly since in that time. I'm going to click over this faint blue signal here. This is was a lava flow from the 2020 eruption, and these are also new lava flows that kind of came in after the 2020 eruption. So you can see you're picking up there is not magmatic, but associated with surface processes and changes as things cool and contract. You can check that these signals are valid by looking from the other look direction. It's a lava flow substance, it's a long-term uplift. The pattern is very similar. We've got a little gap in the time series there. It's quite a small one, but in other parts of the world, those gaps are more frequent. Right, the other functions that you've got in terms of the analysis are a map of coherence, which allows you to pick, for example, a stable reference pixel. If I go back to the displacement and I say, okay, I'm going to look at a little box in the middle of the caldera there, and I'm going to make my reference area, I don't know, a good reference area here might be somewhere like that because it's far away and coherence is quite good. Let's check the coherence of that area. It's relatively nice. The worst place to try and put a reference pixel might be over in this part here where it's a little bit noisier. So let's try that just for argument's sake. Doesn't actually affect the results too much in this part of the world. What if I place it over the ocean? Thankfully, that doesn't work at all. Once you've got a time series that you think is useful, if you want to record it and come back to it or compare it to other data, you put a function to save it as a CSV file and analyze it, compare it to other data sets offline. You have a surface plot, which allows you to look at the signal relative to the topography, which is particularly useful if you want to understand its context. So here you can see that the uplift is primarily within Wolf Caldera. You can see that the lava flows come set down the side of the volcano. And you can see how the gaps in coherence, where we've got gaps in the data, line up with the low coherence zones that you saw in the coherence map. Okay, the other tools we have here are our Sentinel-2 map, which gives us the context. We can see we've got vegetation in the lower coherent zone around Wolf Volcano. You can see that you've got those dark young lava flows right in the middle of the crater. I go back to the plot. If I want to make a profile, I can pick a profile line, for example, right across the caldera, and you can see that the displacement, which is here in blue, isn't really correlated to topography, but it reaches a peak on one side of the caldera floor. I'm spending quite a while on this because I think it's worth exploring all of the tools. I think what we'll do in maybe another 5 minutes is give you the chance to go and pick your own volcano and explore it yourself. This time bar will move these plots along. So if I go back to displacement and time series plot, I like the descending one. Let's go with that. Bottom of crater, right? We can change the time period over which we're looking. You can see the cumulative displacement on the left is changing. So if I only want to look, for example, at the period running up to the eruption, you can isolate that quite quickly and easily just by limiting the time period. If I only want to look at what happened post-eruption, I can move these bars along and look at the uplift period and try and isolate that and estimate the gradient, look at the properties of it. Because this is a really beautiful, clear signal, I think the time series tool performs brilliantly all by itself. In other parts of the world, where, for example, noise is much more of a problem, where coherence is lower, you might actually be best going through and looking at the individual interferograms and trying to assess whether you find them believable first. So this is what the individual interferograms actually look like from which that time series was constructed. And you can see they're all pretty nice, pretty coherent. You do have some noise, you have some ramps going across them, but you can see they're more or less pulled out by the time series analysis. And you can flick through them one by one using the keys. You can drag to any point, and all of these images are aligned. So when you drag the slider there, you get the Gakos corrections for those dates as well. So you can make a comparison to do an assessment. The Lixar products for whichever date that the slider sits on are directly downloadable here. So you can get those interferograms, or you can go to the home page and kind of select through and download them that way. And at the bottom here, we've got machine learning tools, which I'm not going to go into in a lot of detail just now because you have more about that this afternoon. But if you are looking at the volcano and you want to kind of hone in immediately on the part of the time series where you expect there might be displacements of interest, you can sort of flick through like this, and you've got a heat map on the left there, shows you where you've got the yellow colours and the ellipsoids marked out on the image. They're heat maps showing the probability of there being a displacement signal there. So you might want to use that to say, okay, in this time series, I care about activity that happened in this window, and that's actually about the time of the eruption. You can see there's a huge displacement signal very reliably identified. So just for argument's sake, I'm going to show you a different volcano somewhere else in the world to give you a feeling for how well it performs. Go back to the home page with the map. Recent activity as flagged by the ML approach, which is integrated there, is on this site. So you can jump straight to any of those pages. There's information about the catalog information there, and about the flowcharts I showed you earlier on how to use these tools to critically assess deformation all on the website. If we look now at, let's see, let's pick somewhere in Japan. Miyakojima. It's a tiny island, very challenging target. You can see we've got lots of gaps in the time series, although a lot of data are actually processed. And you have a few periods where something has been flagged. Here it's obviously a lot less reliable because the deformation is much lower magnitude. And what you'd really want to do if you cared about a signal here is go through and look at the individual interferograms and decide whether these are in any way reliable or whether they need further correction or further analysis. If we have a look and see if I can find Fuji. Yeah, I think Fuji is a nice one to look at because we've got a fair amount of data there, but it's quite noisy because it's got very, very strong atmospheric signals. So if we look at any point over, you can see you've got these long-term trends which are affected by phase bias and other sorts of noise, and very sort of noisy interferograms, which quite often have this structure associated with orographic clouds and the seasonal variations. And we've got lots of, these are actually false positive detections with machine learning on there. So even for things like this, I think the critical thinking and the critical analysis using that kind of flowchart approach is a good way to tackle the different volcanoes. So let's take some time now for the next kind of 20 minutes or so for everyone to pick a volcano and do some exploring. If you'd like some tips of where the signals are particularly nice, you can have a look at Volcano's, which has had amazing recent activity, and the interferograms are spectacular. Some of the volcanoes in South America, they've got very interesting deformation signals. Hawaii is very good. If you're interested in looking at like instar signals on the edge of detectability, you could try the examples from the Aleutians, some of the ones in Indonesia and Kamchatka. Not all of the volcanoes for which we have data processed are on here at the moment, because we're in the process of trying to come up with kind of automated quality control assessment so that only data which are kind of reasonably well processed become publicly available. If, however, you're interested in getting access to the complete data set, all we ask is that you get a login. So you can request a login through the website, and we can give you that, and you can look at the complete data set as well. All right, I'm going to leave the flowchart up on the screen while you have a look. And if you have some questions, please ask me in the room, and I will come around and have a look at what you're looking at. And hi.
So there's one online about if volcanoes people are looking for not on the deformation portal, is there anything they can do to get it covered?
So not like within the next 2 minutes, but yes, in general terms, you can write to us and make a request. The other thing is that a lot of the data are actually processed, they're just not accessible through the portal yet because we haven't got this automated quality control going. So what you can do is request a login through the portal website. You put in your name and your email address, and then if you log in, you should have access to everything that has been processed but not quality control checked. Okay, good.
I would say, so then, just if you think like see it, judgment. Unfortunately, yeah. Situation. Yeah. 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 Yes. Yes. Yeah. 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 Right. But yeah, that's actually it. I just like when people have yeah, I just make sure it's both of these things. That both of these are separate data. Yeah, it's really so. Yeah. From the beginning, especially when you see. Yeah, it's yeah, that's what I'm trying to. And then it's good for trees. It's not. Yeah, see that. See that. Yeah. So, any other questions in there? Was it good? Yes. I'm looking at it. Yeah, yes, the research group in Manchester, they love it. Yeah. So, have you already discussed it? Oh, well, also. Right. Yeah. Yeah. Because you had something to get this week. And so we were like, that progress, yeah. That's a global message. Global message. Finances for person. And ending this up. I got it. Don't worry. One question, is possible to get data in a better solution because the pixel size is sorry, I'm not asking. It's possible to get data in a better solution because the pixel size of the system should yeah, so that the not online. But you can download the products. So it's download here. The online product speed. Okay, but we can get it in the original. Yeah, so you can get it down for the resolution. So if you go down, so you scroll down the page, then the product speed download. Yes. It's these space and it's simply yes. So so that was it. System highly projecting and response. Not without also, but I guess we have aspiration to try to apply stuff. Yeah, because I think it's not. It's worth the investment. It's a regular acquisition. It's and analysis. Oh, yeah, acquisition strategy. Yeah, well, it's space, general space, also we have sweet, yeah, there's an aspiration to much as it would be. Yeah, so it should be. So the green point is the choosing, the red one is the reference. This minus this. So if you put your red here, you should go this. Where are you looking? Oh, it's a nice big. Sure. You can also sometimes have to nurse and dry so if you click and drag, then you can make it. There you go. That's it. Yes. Where? It's gotcha. That's very good. Does anyone else in the room have some questions?
Yeah, try to explain. Yes.
Yeah.
Yeah. Okay, I think it's great. So we've got coffee outside?
Yes.
Yeah. So if you'd like a break before getting into volcano modeling, now's the chance. But if you're really keen on the portal, you can keep going, of course.